So please.
Yeah, thank you very much. And well, so I will carry on from what I said the other day. So basically, I would like to show how one can use gravitational waves to test theories beyond the standard model. I will talk about first-order phase transition that have been covered a lot during this week, cosmic strings. Then about early universe, second-order scalar perturbation. Already Gian Massimo spoke about that at least, and somebody else, I don't recall who. Stiff equation of state, and I will put a couple of transparencies about parity violation. That's another thing about the early universe. Then I will discuss anisotropies in the gravitational wave background and how it can be used as a way to discuss the large-scale structure of the universe. Then I will discuss about gravitational waves as a tool for dark matter. In other words, cold dark matter with respect to interact dark matter, and I will put constraints on primordial black holes using LIGO-Virgo-Kagra data, and as well to axion-like particles. And finally, I will give some hints about how one can use gravitational waves with or without electromagnetic counterpart to have ideas test of GR. So okay, that's what you have heard quite a lot about first-order phase transitions. So what you of course know is that during the majority of the history of the evolution of our universe, all processes were adiabatic and near equilibrium. However, if you have a process which is non-adiabatic, then that's what you can find interesting constraints, in particular about gravitational waves, magnetic field, baryogenesis, primordial black holes, and so on. So that's something that already before Alberto put, I think, at least Alberto, if not more people, this plot about first and second order phase transitions. And of course, you need only first order phase transitions for gravitational waves. Second order phase transitions are adiabatically, so you do not have a production of gravitational waves. So as it has been already said, you have many models beyond the standard model where you have that your matter field is trapped in a false vacuum. And to go to the true vacuum, this happens through the formation of bubbles. You have bubble nucleation, and then you have, they grow, they merge in the expanding universe. And that's the three ways that we'll discuss that can lead to the generation of gravitational waves. And if you can detect such kind of signature, then you can have some kind of indication of beyond the standard model of particle physics theories. So you have your bubbles which are going to nucleate, which are going to grow. The reactions front is going to be formed. The bubbles and the fronts are going to collide. You have sound waves in the plasma, and you have as well turbulence. So there are three different mechanisms that can lead to gravitational waves: bubble collision, sound waves, and magnetohydrodynamic turbulence. That's a word that I have difficulties to say. It's like any of you trying to say my last name. I have the same difficulty to say this magnetohydrodynamic. I managed. So we're going to discuss the first two. I mean, we consider the first two just because they seem to be the dominant mechanism and because there is no consensus, as far as I know, about the third one. The simulations of the different groups do not give the same results. So you are going to have, therefore, some mechanism which is going to lead to some anisotropic stress tensor, and that it will have a different expression depending on one of these three kind of types of mechanisms for the generation of gravitational waves you have. So let us consider a phase transition at a particular time t star, which is going to generate anisotropic stresses, which will source gravitational waves. The peak frequency is larger than the Hubble rate, and then you have the gravitational waves energy density, which has this form. And depending whether you speak for superhorizon or subhorizon scales, if you have for superhorizon, the spectrum is blue. For subhorizon, the spectrum is going to decay, and the decay law is going to depend on the details of the source. So usually, the gravitational waves from phase transitions have been studied for LISA. That's, for instance, if you have phase transitions between 1 GeV and 1000 TeV. And as an example, electroweak phase transitions at 100 GeV, and that will lead to gravitational waves which are in the millihertz or even lower frequencies, so they are within the LISA kind of detectability. SKA, LISA, Einstein telescope, will be sensitive to first-order phase transitions at around 1 MeV of 1,000 PeV scale physics. However, if the phase transition is between 10 to the 7 and 10 to the 9 GeV, then you are within the detectability of LIGO-Virgo-Kagra, and then you could get some kind of test of physics beyond the standard model at an energy scale which cannot be reached by LHC. So the example that I give here, so everything is going to depend on, usually, I mean, there are several parameters, but the most important ones are the strength of the phase transition and the inverse duration of the phase transitions. These are these two parameters, alpha and beta. And remember, yesterday, I defined the power law integrated curve. So here I give the power law integrated curve. I mean, when we did the study, it was the third observing run. Now we repeat it for the fourth observing run where we are. So the third observing run, then this green line is the power law integration curve, which means the sensitivity curve. And the red one is the design sensitivity of our detector. And then we have two cases, sound waves and bubble collisions. And depending on which values for these two parameters you have, you might be between the detectability of your detector. Now, okay, that's something about the radio pulsars, but that's not interesting now. So the standard model of particle physics predicts no strong phase transition to have taken place. And if we find some kind of signature, that means that we have some hint of beyond the standard model phase transition. So what we did, we considered this broken law, power law, and we consider that we have a contribution of compact binary coalescence, because might not be a phase transitions, but we know that there are compact binary coalescence. So we need to have, for sure, this to the third kind of frequency dependence on the omega CBC. And that is the kind of model that we consider. And we perform a Bayesian search. I told you yesterday about inference statistics, the frequentist and the Bayesian. So we have a Bayesian search. And we search for a broken power law in the presence of a CBC background. And of course, as we said yesterday, when you do Bayesian statistics, you have the priors, and you have to see how your results depend on the priors. The priors we took N1 equal to 3 for causality. For N2, we use a uniform distribution between -8 and 0. Actually, for sound waves, what we know is that most probably is about -4. For BCs, -1. But it is rather more conservative to take, a bigger kind of range for N2. And the most conservative case we took is this delta to be equal to 2. And we searched for that we had this kind of broken power law, but we had as well a phenomenological kind of model by taking results from simulations of what exists in the market. And we searched for something like that in the 01 to 03 data of LIGO-Virgo-Kagra. We didn't find any kind of signature, but we were able to put constraints in both the CBC as well in the sound waves and the bubble collisions contribution. So then one can say, very good, and what about that? Because from the point of view of somebody who has a particle physics models, you should go back and translate these constraints to the parameters of your models. So that we did it consequently. We consider supercooled case of phase transitions. This exists in various particle physics models. The supercooled phase transition is interesting because the phase transition has a longer duration, and therefore you have a stronger kind of gravitational wave signal. So we consider two models, minimally U1 extension of the standard model of gauge group, and the radiatively broken U1 Pechet Queen symmetry. And we were able, from our constraints, to put constraints of the parameters of the model. So now, if somebody is interested from a particle physics point of view, you take your preferred model, and you go to translate the constraints on the omega contribution to the parameters of the model. Good. Second thing I'm going to discuss is cosmic strings. Some things were said here, some things I would like to repeat. At some point, I remember, Thomas, where you gave your talk, you asked whether people know about symmetry, about Higgs models and things like that, and I didn't understand if people know or not, so I will put two slides, but I'm not going to go into any detail. So for people who are familiar with group theory, then what you have to do is you know that you start from a large gauge group and you have symmetry breaking down to the standard model. You study the homotopy group of the false vacuum, and if the K group is non-trivial, then you have the formation of defects with dimensionality 4 minus 1 minus K. So that's the mechanism that you do. And then what we did, as a matter of fact, ages ago, you can see, is that we consider all possible kind of symmetry breakings from a large gauge group down to the standard model. We studied the homotopy group of the false vacuum, and from that we were able to see how generic is the formation of cosmic strings. And we found that it's pretty generic, okay? So there are two types of models that people study. The global strings, global defects in general, and local strings or local defects. And usually when people say local, when people say cosmic strings, we mean local defects or one-dimensional defects. So this is the standard mechanism that you have for a Goldstone model, which is the global string. Both they have same kind of formation mechanism, but as we will see, the properties are slightly different. So phi is a complex scalar field. V of phi is the Mexican height potential, and what you find is that the minimum of the potential, they lie along everywhere in a circle for which only the radius is fixed and not the position, okay? And the position is what, where you see symmetry is broken. If you have that your symmetry is a local gauge symmetry, so that's the Lagrangian, this is the covariant derivative, F nu nu is the field strength tensor, and again you have the Mexican height potential, then again, you have that the minimum of the potential, they lie or in a circle where only the radius eta is fixed and the position theta is arbitrary, okay? So symmetry is breaking. So now, so how do you find where you have the formation of these cosmic strings? If you take a closed path in a physical space, okay, and the total change of the phi field, of the phase of the field is 2 pi, and you try to shrink it at a point, you cannot do it continuously without arriving to a point where the phase is undefined. That means that the cosmic strings are infinite or there are closed loops. So any string must be either closed, which we call it a loop, or infinitely longer, okay? And therefore we say that in any, around any, within any path, any circle path around which the total change of your phi is equal to 2 pi, it is enclosed a cosmic string, which has to be either closed or infinitely long. Now, just to give you an idea, the only important kind of quantity you have is the tension of the string, which is characterized with the temperature of the phase transition at which strings were formed. So this energy scale is given by the tension G mu. Mu is the linear mass density. So when I'm saying about GAT strings, they were formed at the GAT scale. That means that they have a width of 10 to the minus 32, and I have a tension of 10 to the minus 6. Okay, so that's in order to keep in mind what the scales can tell us. And if what we do, we put constraint on the tension of the string, G mu. That means that we put constraint on the temperature of the phase transitions at which these objects were formed. And at the formation, 80% of the strings are infinitely long. They go in and out of your box, and 20% are closed loops. Okay, so that's what you have. Now, the strings, they have a point where instantaneously they propagate at the speed of light, which we call it the cusp. Then because strings, they intersect at points, okay, they exchange partners, and then they form this kind of discontinuities, which we'll call it kink, okay? And kinks appear in pairs, and we will have emission of gravitational waves from the cusp, from the kink, and from the kink-kink collisions. So the strings lose energy, okay? This is the rate at which they lose energy as they oscillate, and this is the frequencies of their oscillations. So finally, the characteristic frequency is inversely proportional to the length of the string. So then the strings, they lose energy at this G mu square. A gamma is a constant of the order of 50. And like that, the string, they have a lifetime which is inversely proportional to the tension of the string. Okay, so they have they don't live forever. So then we know that they emit gravitational waves from the kinks and the cusps of the strings. at the frequency at which our detectors today operate, the gravitational wave backgrounds from cosmic strings is produced from strings during the radiation-dominated era. And remember, everything I say goes basically for LIGO, Virgo, Kagra kind of detectors. So then we know the frequency, this is the frequency of the gravitational waves, but we know that we can calculate the energy density of gravitational waves either from this omega that I said before, either from this omega here, okay, or is equivalent to take the number of cusps you have. This is an old work by Vilenkin and Damour. So usually instead of calculating the oscillations, we calculate the number of cusps we have. And there is an agreement between the two for a gamma of about 50. This gamma that goes in this expression there. No, the kinks, here it is. The kink is going to, the gravitational wave from the kink is going in this kind of conical kind of direction. Yeah. So the kinks and the cusp, that's why I have this angle here. It doesn't, it's like a kind of lighthouse. It goes to this conical direction. And if you are within this direction, it moves around, you receive it. So it's not all, kink, yes, but cusps and kinks has a directional. What is what? L is the length of the string. Of the loop, is a loop. Yes. Yes. Sorry? The number of, no, we consider the number of loops of a given size. Okay? Now, this I take here one loop. What you see here is one loop. What I'm saying here is the frequency, the angle, it is determined by the, for gravitational waves emitted by one kink or for one cusp of a loop of a given size. Yeah, I don't know. I don't know if it's like Sikhodon, but that's. So then we know from this paper of Damour and Vilenkin what is the waveform of gravitational waves emitted from cusp, from kink or kinky collisions. And immediately from here, you can see that if the number of kinks is not many, then cusps wins over kinks. If the kinks are many, then kink-kink collision wins. And that's exactly what I told you before. Kink-kink collision is isotropic. For cusps and for kinks, it is beamed along this angle that we defined before. So then you go to calculate the omega GW. Remember yesterday, or I don't know, 2 days ago, I gave the omega GW for the case of compact binaries, and I told you that it depends on the mass, on the spin, of the type of range. So here it depends on something that I will get from my numerical simulation, which means this quantity here, which tells me how many loops I have of a given size, the number of kinks, and the number of cusps. This is the input that I put from my model, from my numerical simulation. And then I have only one free parameter, which is the G mu, which is the tension of the string. Okay. In the market, there exist two models. The model B, which is our model from 14 years ago, with Christophe and Larissa. And then there's another model, Blanco Pillado et al. And then, since there is a disagreement between these two models, we came up again with Christophe, with Daniel Stier and Pierre Auclair, to a kind of a semi-analytical model, which interpolates between the two. And now the collaboration and everybody studied these three models. In the past, people were using the old one-scale model of Kibble. That means that all the loops have the same size. Of course, this is not the case. So the models which exist now are that, plus whatever people do in field theory simulations. But the field theory simulations have not reached the same level of development in order to be able to see how many strings we have, the loop distribution. So then, remember yesterday, I defined how we look for the posterior, the probabilities and all that. And remember what I said yesterday, that my data, LIGO, is going to give me this 2-point correlator factor, which I defined 2 days ago. My study is going to give me this, which is given a model M, one of the three models. I go therefore to calculate the omega GW, and the only free parameter will be the G mu. And then we looked for that in the data. And what we have found is the constraints which you can see here. These are the constraints, the most stringent constraints which exist for the case of the cosmic strings. You can see here, we have the model A, the model B, and two variants of the model C. These are the two numerical models, and this is the interpolated analytical model. Here I have, what do I have? I have many kinks. That's why you see that what wins is this blue line, which is the king-king interaction. Here I have one kink, so what wins is the cup interaction. And these are the models, these are the constraints which we have reached. These are the most stringent constraints we work for the tension of the strings. Now, and if you want to see to what they correspond, that's it. And remember that from CMB, we had constraints just for strings at the GAT scale, which means 10 to the minus 6. Now we went down to 10 to the minus 15. Okay? Now, information about the early universe. Okay, remember what Gian Massimo said a few days back for the second order scalar perturbation that can lead to the formation of primordial black holes. Okay. Now, you have like that a strong gravitational wave background, which is created at second order in perturbation theory from your scalar perturbation. However, at large scales, there are constraints from CMB, which tells you that it should be of the order of 10 to the minus 9. And therefore, the background which you are going to get is extremely weak, so you cannot detect. However, if primordial black holes are formed during the radiation-dominated era, then this kind of curvature power spectrum needs to be of the order of about 10 to the minus 2. And therefore, the gravitational wave background can be within the detectability of your detectors. And there are various models of inflation which lead to this kind of peak in the spectrum, 10 to the minus 2. So now the idea is, so let me take just to give you the definitions. Let me write down my metric, okay, which I split it into a linear level and some nonlinearities. And therefore, these nonlinearities is the mixing of the three modes, and these are going to lead to the second order tensor modes. Now, what you can do is, if I know the power spectrum of the curvature perturbations, then I could get what is the power spectrum of the induced gravitational waves, and by knowing that, I can find the omega GW. The relation between the power spectrum of the primordial curvature perturbation and the power spectrum of the induced gravitational waves, it is given here. Having that, I can go and find what it is the omega GW, and here is the omega GW. So what I'm going to do, I'm going to model the power spectrum of the primordial perturbations, from which I will be able to detect what is the omega GW. And because I don't like to take a particular model of inflation, we take this kind of log normal shape for the peak of the curvature perturbation, which is depending on the location of the peak, of the position of the peak, and the amplitude of the peak. And then we go to search for some kind of signature in the data. And these are the kind of excluded regions which we have found. The LIGO Virgo, you see, it's already better than the BBN or the CMB. This will be the LIGO design sensitivity, and this will be Einstein telescope. So already the constraints which we can be put in the amplitude of the power spectrum are stronger from what already existed from BBN or CMB. They can be even better as the interferometers reach their sensitivity, design sensitivity, or third generation interferometers. And this can put constraints in the corresponding inflationary model from where these things could be generated. Now, stiff equation of state. There are several particle physics models which say that they might be a kind of stiff equation of state, which is between the matter-dominated era and the new radiation-dominated era. So I start with, I have inflation. At the end, I have radiation era, matter-dominated era. Then I have an era, exotic one, with a stiff equation of state, which means that the relation between the energy and the pressure is between 1/3 and 1. Radiation-dominated, matter-dominated era. And there are various models motivated from string theory or beyond standard model physics that tell us that this can happen. Now, then we can see which is the gravitational wave spectrum that we could have in case this kind of exotic era existed. And what we find is that the stronger results, they come for what is called kination. That means that the equation of state is equal to 1. And you can see from here that if I have the inflation could be this dotted line, and now if I have the stiff equation of state, this is the kind of spectrum which we are going to get. So already we can put from the LBK data constraints in models where the kination frequency is above 10 Hertz. The matter dominated to kination is above 10 Hertz, and the kination here to the radiation is, has to be smaller than 10 to the minus 5 Hertz. So already from the data we have, we can put constraints on the duration and the position of this stiff equation of state, which means I can put constraint in particle physics models that they can tell me that. I don't know why it doesn't go on. Okay, now, parity violation. As you know, there is a matter-antimatter asymmetry, okay, in the universe. You have the Sakharov kind of criteria. That means that at some point there could be an early universe mechanism that can give what is called amplitude birefringence, which means that you have an asymmetric amount of right and left-handed circularly polarized gravitational wave background, okay? It's pretty difficult. We don't know of mechanisms that can lead to this kind of parity violation from astrophysical sources. And therefore, if I can detect this parity violation, then I could have a hint that my gravitational wave background is of cosmological and not of an astrophysical origin. So if you do, to study for that, remember yesterday or 2 days ago, I found this 2-point correlator for the strain. Now it's going to be of that form, where it is expressed in terms of the Stokes parameters I and V, which in the case of unpolarized is equal to 0. So when I write my omega GW, it will have this contribution, which is from this polarization, where this polarization degree is this pi, okay? Which again is the relation that you get from the Stokes parameters. So if I have no polarization, this pi equal to 0, and fully right or left, it will be minus or plus 1. Then we looked for that in the data, okay, in a generic kind of search, and we did not find any kind of hint for this parity violation. Then, yeah. This is the standard omega of GW, okay? So here, I come here. This is the total omega. This is omega prime, okay? So this is my unpolarized. This is the gamma is the overlap reduction function which I have defined 2 days ago. Okay? You remember I have defined this overlap reduction function, which has to do with the response of the detector. Depends on the geometry of the orientation of the detector. So now it will have a dependent whether it's right or left, and that is the extra term. These are the detectors. D1 is detector 1, detector 2, and this is the corresponding from the Stokes parameter, gamma. I don't give the value. So it will be this extra kind of contribution to omega, which comes from the polarization degree. Yeah, the omega will have a specific, the omega from CBCs is 2/3 with nothing. Now we'll have a specific feature. We looked for that. Let me tell you how it will. Okay, we looked for that in the case of a power law, okay, with a generic value for pi, and we didn't find evidence. Then we tried to see for some specific kind of model, and the model which we consider is helical turbulence in the early universe, and this is the model by Axel and Tina in 2020. So where we model the turbulence like a broken power law, and this broken power law, this value of the position where the power law changes, it will depend on what is the frequency, and that will lead to a parity violation degree, which is frequency dependent. And what we found is that, as a matter of fact, there is a polarization which is okay in order to find the signal of parity violation, but in order to measure how big is the parity violation, we need this to be even bigger, which means that seems to be that even if we detect a turbulent signal, we may not be able to deduce its polarization. So it's something very difficult, at least with current detectors to do. Now, then I would like to talk about anisotropies in the gravitational wave background and large-scale structure. So what is our plan? Is to do the corresponding of what people have been doing for years in the cosmic microwave background. So instead of taking the two-point correlator of the temperature difference between 2 points of the skies with separation theta, we found the d omega at 2 points of the sky, which means if what I said yesterday and I defined the two-point correlator of the strain, here this omega is going to have a frequency, a directional dependence. So I'm going to write my FLRW metric, okay, in this form. My scale factor, the psi and phi are related to the Bertin potential, the standard thing that people do. And then I'm going to define the majority, whatever I'm going to say, it will be just taking into account which exactly what everybody does, and then I tell you how we went beyond that, the kind of an anisotropy, which is due to the anisotropic distribution of the source. And then I'm going to consider the peculiar free velocity of the cosmic fluid. Having that, I'm going to define what is the gravitational luminosity emitted at a given frequency, which depends on the parameters of the model. For CBCs, this is the mass and the spin, and this is the rate of mergers, all these things that I said 2 days ago. Then I'm going to write down what is going to be the energy density that we're going to have of gravitational waves per frequency interval and per solid angle around my source, okay? That's how it's going to look like. And now, this is the omega GW. This is the omega GW. And in the context of FLRW universe, this is the expression that you get if you want to have the full expression of that. Now, we are going to consider that there are perturbations in this background. So it's going to be the unperturbed omega bar plus this small perturbation that you have here. And I'm going to relate the strain and the luminosity through this expression here, which is this is the total energy of gravitational waves radiated from the source. This is the rate at which the signals are emitted. And then you can find what will be the total energy of gravitational waves. And from there, you can find the luminosity. Now, the final expression for the energy density of gravitational waves, it is this form here. It is conformal time. This is the scale factor. These are the integrate over all parameters. For CBCs is the mass and the spin. For cosmic strings, for instance, is the G mu. This is the average of the number of objects I have. This is the rate of the mergers. This is the anisotropic in the number density. These are the Bertin potential, and this is the anisotropic stress tension. Here is, for example, for people you remember, the integrated Sachs-Wolf effect corresponding. Now, I'm going to consider only the anisotropies due to the anisotropic distribution of the sources, but I'm going to consider only as well the kinematic dipole, because this is important, and as you have seen, it plays an importance in the calculation at the end. So this is the corresponding term that you are going to have in that way, okay? Of the energy density of gravitational waves. Then I do the standard thing that everybody has been doing for the CMB. This is the total isotropic background. This is therefore the anisotropic distribution of the omega GW. I form the two-point correlator, okay? The two-point correlator, if I assume that I have Gaussian statistics, is all I need to know. From there, I can do a multiple expansion in Legendre polynomials, which is exactly what people have been doing for the CMB. And then the anisotropies are given by these CLs, which give you an isotropy in L, which goes like 2 pi over theta. And these are the Legendre polynomials. So that's what we found. by considering the only available galaxy catalog, we were able to do the corresponding of the CMB map for a galaxy distribution, okay? And this is what we have found. It's interesting to notice that if you take different astrophysical models, they will not give difference in the anisotropies that you are going to get. We found that for CBCs, we found that for cosmic strings as well. Now, there is something to keep in mind that before was said as well about how data can tell us something about anisotropies. Unfortunately, you see, for me, I went up to L of thousands here. I can do it. The point is that in all the papers of the collaborations, you will see that we go to very small L. If we consider CBCs, we go up to an L of 4. It's ridiculously low. The problem which we have, and there are various ongoing studies to go beyond that, is what is called the diffraction limits, which relates the sensitivity in the angular separation of your detector with the distance between the detectors and the frequency at which the detectors can work better. So this is a constructed kind of issue that you cannot do much. So people are trying to to somehow overpass, but this is ongoing issue and ongoing studies, and that's why in all the papers of the collaboration, we stop at this very low L. Now, okay, what is that? This is, I think, the case of cosmic strings. We're able to do the same, so we have the same maps of the sky for the case of anisotropies of cosmic strings, which is good. Now, in all that, however, as I said before, we did not take into account that these gravitational waves, they come in a background which is perturbed. So there are the propagation effects. The propagation effects we consider in these two papers, which, as I said, it's actually a couple of us from London, and they were our friends and colleagues from Padova. So we did these two studies. One is actually a numerical simulation. This is a public code where you can put the particular model that you want, and you can calculate which will be the effect of the propagation of the gravitational waves. There is another more important effect, which we found more recent, a bit later, which is what is called the temporal shot noise. People who do astrophysics know very well that there is a scale invariant term, which, as you can see, it's dominant, which actually is the effect of having a finite number of compact binaries, which means that all the way of calculating these anisotropies that has been done so far is going to calculate that, which is completely off. This radius R, star, if you wonder what it is the scale below which I can forget the contribution because there are transients that have been detected. Okay, so no matter what you put for this value R, unfortunately, you find that this is a biased term that is going to screw up whatever calculation you do. And as a matter of fact, we did several maps of the sky with that, and seems to be that indeed you lose everything. So what can you do? Later, in a series of papers, we came up with a new way of calculating the anisotropies by cross-correlating gravitational waves maps from different kind of segments, more or less like the same thing we were doing for the isotropic background. And then we built a new minimum variance unbiased estimator, which now for first time we employ within the fourth observing run of the collaboration. Okay, now, what I want to say beyond that. Yeah, then more recently we said, okay, let us try a kind of complementary approach. So far what we have done, I take my galaxy catalogs, I locate where my compact objects, and from there I can go and trace the anisotropies. But I could do that without data from catalogs, so without electromagnetic data. Why? Once I will have by far too many data of gravitational waves, I can use them to study anisotropies. So we develop a method, which of course now the results are premature because we did not, you need very good localization. So we need to take the data for which we know the 3 interferometers worked. So we took this data, for this complementary approach, we probe the spatial distribution of BBH merger events by computing their observed angular power spectrum and then comparing to isotropic distribution. By doing that, with the current data that we have up to the third observing run, no evidence for anisotropy in 2 sigma confidence level. Once the data will become much bigger, I believe that this approach will be rather powerful and independent of any galaxy catalogs. So now what we do right now is we try to develop that for 3G detectors, and also we try to estimate an important question: what is the minimum number of events I need in order to confidently be able to find an isotope? Okay, now I have the events that I have, it's not sufficient. What is the number of events I need in order to do that? Now, let me say a few things then about the kinematic dipole, because it was this discussion before. So we did the targeted search for the kinematic dipole of the gravitational wave background. So you have a contribution from the time-independent solar dipole, but you have as well a kind of time-dependent contribution from the orbital dipole. It's the orbit of the Earth in the perihelion. This is time-dependent. This is the important contribution, but this one will make as well a kind of influence of about 10%. So here is the kinematic dipole, which is related to the omega GW. For instance, for the case of CBCs, that's what you get. The kinematic dipole is going to generate at a contribution to the L1 multiple, which is your background, okay, which is given here. So that is finally the result which you get. This is the orbital period, okay? And what we have found then we built a pipeline which is used from the collaboration now, based exactly on what I told you before. By correlating the data from different times length, we were able to build this unbiased kind of minimum variance inference for the dipole magnitude. And what we have found is that, for instance, third generation detectors, they are going to be able, for the alpha, for the red one, which is 2/3, they will be able to detect the dipole, which is here, extremely quickly in about less than 2 days of data. Now, gravitational waves and dark matter. So, as it is known, there is an evidence for existence of dark matter. We have this evidence from the flat rotation curves, from the cosmic microwave background, and there is a variety of models that have been studied in the past. What seems to be more valid now is primordial black holes or action-like particles. There have been some proposals for modified gravity models, these tensor vector scalar models, all that, they have failed. So up to now, I mean, they need a lot of fine-tuning, so they have failed. So what seems to be is that either there is another kind of gravity theory that we don't know, or that indeed probably is one of these kind of contributions there. So the idea is it is or it is not. How can we use gravitational wave data to put constraints to that? So the first thing that I would like to say is how we can make the distinguish between the type of dark matter. It's called dark matter or some kind of interacting dark matter. The present observation on supergalactic scales, they are okay with the definition that dark matter it is cold. So these are the type of cold dark matters you might have. But the important kind of ingredient is, in order to discuss what is the nature of dark matter, should be in subgalactic scales at large redshifts, okay? And that is going to depend a lot on the type, on the nature of the microphysics of the dark matter that you consider. And there are 3 different types of dark matter, therefore: warm dark matter, interacting dark matter, and fuzzy dark matter. Whichever of these 3 you have is going to give distinct kind of signature than cold dark matter, because generically it predicts small scale signatures that are different from the predictions that you have from standard cold dark matter. And as a matter, there is a big kind of problem for many years that simulations predict more scale, small scale structure than what it is observed. So then what we did, we say, okay, let us consider a kind of model, a toy model of interacting dark matter, where we have a dark matter neutrino, which is interacting with a kind of this particle that through this dimensionless interaction strength. And what then we want to calculate? The rate of mergers. And we calculate the rate of mergers, as you can see, that this is the rate of mergers that you get, and this is what cold dark matter is going to give you. So there is a big difference, in particular, as you go to large redshift, and this difference is going to be something that third generation detector will be able to detect. LIGO Virgo lies here now, okay? So third generation detectors will be able to see the difference if it exists for large redshifts, and therefore to identify distinction between cold dark matter and an interacting dark matter model. So that's something that will come from the mergers. Now, what about axions? So that's one of the models. Can we put constraints on axions? So I don't know how familiar people are with all these models, but just give a bit of idea. So I'm going to take axions coupled to nuclear matter in a similar way with a QCD, but their mass is quite low. So if you have these axions inside a dense object, for instance, neutron star is by definition a very dense object, then the potential of the axion is going to get this finite density correction. Then, if the radius of this object is greater than a critical density, then a phase transition is going to happen, which is going to lift to shift the minimum of your potential from a zero to a non-zero value. For the case of a dense object, that is this critical radius at which this will happen. This is going to lead to a new scalar kind of force, which is going to be attractive or repulsive, depending whether we have the same or opposite kind of charge on these two neutron stars. And this will be this force. Okay? That means that if you have such binaries within which there exists such an axion field, and they form this binary, these neutron stars, then you are going to have an extra kind of axion waves which are going to be radiated. And then if you have this extra kind of radiation, you can try to calculate what is going to be the correction in the dynamics, in the radiated power, and the gravitational waveform. We have done that before the BNS discovery with an effective field theory approach, and we found that advanced LIGO will be able, by studying that, to put constraint of axions with mass smaller than 10 to minus 11 eV, and in this kind of range, if it is the decay constant of axions. And then, luckily enough, we had the GW17 OH17, where now this is your waveform, and then you are going to have that the phase is going to have the standard phase of the GR, plus a leading term that comes of the axion field, and then you have the post-Newtonian kind of corrections, and these are the constraints which we have found, okay? And these are in relation with the BBN, with superradiance, with whatever astrophysical constraints exist. So these constraints will become much bigger if more data come. So up to now, we were able just with one constraint to put with one detection, the GW17 or OH17, to put constraints for axions in the mass of about less than 10 to minus 11 eV, and with a decay constant between these two levels. And without, this is a constraint without demanding that axions play any role as dark matter. Primordial black holes. So, okay, as you know, this is the mass of primordial black holes around the horizon mass. They evaporate on this time scale. I will define by f of m the fraction of dark matter in primordial black holes of mass m. These are the typical types of primordial black holes that you can have that are still, that could be still unconstrained from the data: asteroidal to subluminal range, intermediate range, and extremely large range, which are irrelevant from dark matter. And what gets a lot of interest is that if you have between 10 and 100 solar masses, then it could be the ones that we study from LIGO. So what we did, actually we finished a couple of weeks ago, is for the first time taking real data of the 3 observing grounds and go to calculate for the case of monochromatic, but as well because monochromatic is really not that physical, an agnostic log normal Gaussian distribution, which is given here, okay? We went to calculate, to put constraint on this parameter f by using 01, 203 data of the LVK. We consider 2 cases, the early and the late binary formation. Early ones are the ones where these binary primordial black holes were formed at the radiation-dominated era. Late are the ones which are formed much later during the clustering of black holes in the matter-dominated era. The early ones are the ones which win. And here are the constraints which we have found. This is the current constraints which we have found by using 01 to 03 data. Now, then I'm going to say a few things about, unless people have questions or I have another 29 minutes, which I'm not going to use the 29. And if people don't have questions, people probably are tired. So either I continue with that or I don't know if people are interested to hear that or not. If not, if people are tired, I just stop here. If people want me to go on, I will go on. But I realized from just looking at people that you lost contact with me or I lost contact with you. At this point, I'd rather stop here. Any questions?
Also, the question is that
Yeah. 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 No, I just take the scalar radiation that I will have action. Let's say the standard gravitational waves plus the scalar radiation. That's how, because that's what I can put constraints. Constraints I can put from that. I mean, I have data which comes from the from this binary neutron star. So I use this one to put constraints. I want to use gravitational waves, and therefore I don't consider another. Yeah. If you change what? Yeah, certainly. There are. And there is an excellent paper about Sir Simon's gravity. There is a paper, I have the slides, but then I thought not to overput it. There is an excellent paper from, now it slips my mind, but I know this guy in the US about Sir Simon's gravity. And I know of 3 papers that do that. A paper by this group that I can tell you it will come to my mind, Sir Simon's gravity. There was a paper for axial inflation from Mohanty et al. And then it was our paper where we tried to do it. So that's all I know for the parity violation from Cosmological. Then there have been some studies of people that an isotropic distribution of astrophysical sources could lead to parity violation. And that's a paper by the Padova group, which I don't, I mean, I don't know exactly, I couldn't understand exactly how this parity, I mean, but there is this approach that could be. So either it's cosmological origin, or it could be from astrophysical, from like a second order effect. It's an isotropy and lead to a parity violation. Sorry? Yeah, for CBCs, we did the study. We did, I mean, parity violation from CBCs, you're not going to have, basta, that's it, you cannot. So you need another ingredient. So then when you go to find, as we did, if I have CBCs plus a cosmological thing, that gives me parity violation, I go to search for that. We couldn't find any trace of that, okay? But it depends as well very much of the orientation of your interferometers, as you understand. Yes. I couldn't understand at all what he said. Yeah, I put for a given mass, as you can see here, for a given mass, I can put constraint on the inverse of the, of the axion decay. Yeah.
So is it about QCD action or general ARBs?
No, this was for a kind of pseudo-scalar, which is like the QCD with smaller mass than the QCD.
Okay.
That's all. I don't take anything of, I don't take, if you can write the potential of that form,
okay,
then it's fine. With the first, the green part is the correction which you have inside a compact object, inside somewhere a dense object like a neutron star. You have this correction, but it's like it's like a QCD axiom.
Okay.
If you accept the mass to be low.
Yeah. Then another related question is are you assuming the action consists of a whole the amount of dark matter in this analysis?
I don't put any constraint here that this action plays the role of dark matter.
Okay.
Less. So this is independent of what is the role of action.
Okay.
It could be, now, if you want the action to be a dark matter, and then your dark matter requirements accept an action of the mass that I can find here, then we are in business. We're here. Constraints on actions below the 10 to minus 11 eV. If you think that such actions could play the role of dark matter, I'm fine. If they don't play the role of dark matter, too bad. But what the constraints we found from only this one event are for such an action.
Okay. Thank you.
So maybe following up this question, so do you assume some specific axion nucleon couplings, or is
No. That's all is all that I have here. These are free parameters. Parameters is not the no. I don't assume anything else.
Okay, but axion needs to interact with neutrons, right?
Yeah, they are inside the compact object like a neutron star. For me, yes. Otherwise, they will not have this correction.
Yeah, exactly. So the strength of
that's all that I need. I don't have any coupling anywhere. I'm saying that if they're inside the compact object, there will be extra corrections. And then I'm saying that if, where is that now? If the radius is greater than a critical value, which is this one, then you will have the phase transition, which will bring it from 0 to this non-zero value inside the dense object. For a neutron star, where we know that the radius is about 10 kilometers, then this happens for actions of this kind of constraint for the action decay constant. That's all I'm saying. And then if this happens, I'm going to have an extra force, a scalar force, which is this one, which will be plus or minus depending on whether they have the same or different charge. So it's something that normally is not something special for a neutron star, given that it's compact, given that the radius is about 10 kilometers. So it's a context which normally can exist. Yes, exactly, yes. That's exactly.
Any questions and comments further? Okay, so if not, so let's thank the speaker. Thank you very much.